Hello, in today's video we're going to continue our discussion on section 6.1, Exponential Growth and Decay. I'd like you to go ahead and take a moment and start off by pausing the video and practicing these first four on your own. If we plug in a couple points, we'll go ahead and be able to determine which graph matches with which equation. If I plug in an x value of 0, my y value is going to be 2 times 5 to the power of 0, which is 2 times 1, which is 2. So this point 0, 2 will be on the graph of my function. So 0, 2, we are counting by 2's along this vertical axis, so that's going to be here. From there, the only two graphs that go through that point are a growth function and a decay function. Well, the growth function means that my base is going to be larger than 1, and that is what I have here. So this graph is going to be the graph of C. My second equation, I'll go ahead and plug in a 0. So y equals 3 to the power of 0, which is 1, meaning my graph goes to the point where x is 0 and y is 1. So 0, 1 would be here. And then again, I have a, which is a decay function, and d, which is a growth function. Since my base is greater than 1, I do know that my function will be a growth function, meaning that my graph will be D. Number 3, I have a decay function, and I know it's decay because this base of 1/3 is less than 1. If I plug in a 0, I've got 1/3 to the power of 0, which is 1, so I have the point 0, 1. 0, 1 is here, and it is decay, as we've already talked about, which means my graph must be A. And then lastly, I have another decay function because my base is less than 1. So if I plug in a 0, I would get 2 times 1, which is 2. So my graph goes through the point 0, 2, which would be here. And we did already say it's decay, meaning my graph must be B. We're going to talk about some exponential models, move away from the graphs and into some applications. We have a growth model or a decay model. We've already talked about growth models having bases that are larger than 1. So for example, something like 6 times 7 to the power of t. That base is larger than 1, so it is a growth model. So we're starting with 1 and we are adding some value. For decay, we are less than 1, so something like y equals 6 times 1 over 7 to the power of t. The base of my exponent is less than 1, so we start with 1 and we subtract some value in order to get to that base. In example 2, we'd like to determine the value of a car after a certain number of years. The value is given by this function, and we are first asked to tell whether the model represents exponential growth or decay. To determine this, all I do is I look at the base of my exponent, 0.85. Since 0.85 is less than 1, that means this is a decay function. So as we move forward in time, the value of the car decreases. Identify the annual percent increase or decrease in value of the car. Well, if we were multiplying by 1, the value would stay the same, but we're not. We're multiplying by 0.85. What we are going to do is take that 0.85 and compare it to the base of our model. And what we're looking for is the value of r. So 1 minus r is the base in our formula, and the base in our question is 0.85. So what we're going to do is write this equation and solve it to find r. So negative r is equal to negative 0.15. Divide by that negative 1. And r is equal to 0.15, or 15%. So this car decreases by 15% every year. This is our decay value. In part C, we are asked to estimate when the value of the car will be $8,000. So we are going to input this $8,000 in for y, but we do need to be careful because y is the value of the car in thousands of dollars. So when we plug in our value for y, y is thousands of dollars, so we are going to plug in a value of 8, and that will represent $8,000. So 8 equals 25 times 0.85 to the power of t. And I'm going to solve for the t by first dividing by 25. I get 0.32 is equal to 0.85 to the power of t. And at this point, I'm not able to rewrite the left and the right with the same base, so I need to use logs. Base of 0.32 will equal my exponent of t. So log with a base of 0.85 of 0.32 will equal t, and we use a calculator to evaluate this. In doing so, we find that t is just about 7, meaning it's going to be about 7 years until the car is valued at $8,000. Go ahead and take a moment, pause the video, and practice this one on your own. The base of my exponent is 0.9, which is less than 1, so this is a decay. To identify the annual percent decrease in value of the car, what I'm looking for is the R value that gets me to 1.9. So I start with 1 and I subtract my R value, and that will give me 1.9. So we're always comparing to a starting value of 100% or 1. So to figure out how much I'm subtracting, I subtract my 1, negative R is negative 0.1, divide by negative 1, and R will equal just 0.1, or 10%. So this has a value of 10% decay. To determine when the value of the car is going to be $8,000, what I'm going to do is take my 8,000 and input it for y. Now remember that y is in thousands of dollars, so here y is 8. 8 equals 25 times 0.9 to the power of t. I divide by 25. 0.32 will equal 0.9 to the power of t. Since I'm unable to write these as the same base, I go ahead and I'm going to use logs to rewrite. Log with a base of 0.9 of 0.32 is going to equal t, and we plug that into our calculators. I'm getting about 10.8 for my value of t, so I'll go ahead and round that to in about 11 years, the car will be valued at $8,000. To write an exponential model, we're just going to do the same thing in reverse. In 2000, the world population was about 6.09 billion. During the next 13 years, the population increased by about 1.18% each year. Write an exponential growth model giving the population in billions t years after 2000. So exponential growth is modeled by the function y equals a times 1 plus whatever your growth rate is to the power of t. A is your initial value, and 1 plus r is your growth rate. So to write the model, I'm going to leave y and t in the question, but I need to replace a and r. Well, my initial value is 6.09 billion. We are leaving it in terms of billions, so we'll leave it 6.09. And we are increasing by about 1.18% each year. So as a decimal, this would be 0.0118. So my growth model will be 6.09 times 1.0118 to the power of t. All we did is we input our initial value and our percent of growth. Then to estimate the population in 2005, we started in the year 2000. T is our time, or the time that's gone by since the year 2000. If we want to look at the year 2005, that means that t is going to be 5. So I input that 5, 6.09 times 1.0118 to the power of 5, and then we use a calculator to do the computations. When I do my power here, I get 1.0604, and we're multiplying that by 6.09 to get y. And I'm getting about y equals 6.4579. So the estimated number of people in the world in the year 2005 would be 6.4579 billion people. To estimate the year when the population was 7 billion, well, now we're inputting a y value of 7 and we're solving. So I take my same equation, I put a 7 in for y, 6.09 times 1.0118 to the power of t, and I solve for t. Divide both sides by 6.09. I'm getting a value of 1.1494 equals 1.0118 to the power of t. And now, since I'm trying to solve for the exponent, I go ahead and I use logs. Log with a base of 1.0118 of 1.1494 is going to equal t. And we put this into our calculator. And this gives us 11.8695 if we round. And I will say that we're talking years, so in about 12 years, the population will be 7 billion. Go ahead and take a moment, pause the video, and try number 6 on your own. So now we're assuming that our population is only increasing by 1.5% each year. So our growth model is still going to start with 6.09, but then we have 1 plus only 1.5%, so 0.015 to the power of t, or y equals 6.09 times 1.015 to the power of t. We have our equation written, that's part 1. Part 2, estimate the year when the population was 7 billion. And again, since we're already talking in billions, I just put the 7 in the y spot and I solve. I divide both sides first by that 6.09. When I do that, I've got 1.1494 is equal to 1.015 to the power of t. And then we use logs to solve for t. Log with a base of 1.015 of 1.1494 is going to equal t. Plugging this into our calculator, I'm getting 9.3521 is equal to t, meaning that the population will be 7 billion in about 9 years. The last topic we have to cover is on exponential growth with finances. So we're going to talk about interest, compound interest. Interest is the money that a bank either gives you or charges you depending on the certain type of accounts that you have. Compound interest is interest that the bank is going to give you over a certain period of time in given intervals. So P is going to be the principal or the initial amount in your account. R is the percent that the bank is going to give you. N is the number of times the bank is going to give you your money over that certain period of time, or the number of compounding periods. T is the time that has gone by from beginning to end that your money has been invested. So if I'm looking at example 5, I see an amount of $9,000 deposited. That's an initial deposit, so that's a p-value of 9,000. It pays 1.46% interest. That is my rate, R. 1.46% would translate to a decimal of 0.0146. We want the balance after 3 years, so time is going to be 3, when the interest is compounded quarterly. Quarterly, just like a quarter, means 4 times over the course of the whole year. So my n, or the number of times that we are compounding, is going to be 4. 4 times in 1 year. They want the balance, the final balance, which would be A, after the 3 years. So A is equal to my principal, 9,000, multiplied by 1 plus 0.0146, all over n, which is 4, to the power of 4, multiplied by our time, which is t. Then we go through with the calculator and do these computations. The first thing I'm going to do is work inside the parentheses with my fraction. 0.0146 divided by 4 is going to be 0.0365, and then I add 1, and inside the parentheses is 1.00365. My exponent, 4 times 3, is going to be 12, so I'll do that step next. I take my base and I raise it to the power of 12, and I get 1.044, I'll round that to 7, 1.0447, and then we need to multiply that by our 9,000. Multiplying by 9,000, I find my final balance is about $9,402.21. Go ahead and take a moment, pause the video, and try that next one on your own. You deposit $3,000, so P is 3,000, into an account that pays 1.25%, so R is 0.0125. Compounded monthly, N is the number of times it is compounded in a year. Monthly, there are 12 months in a year, so N would be 12. What we want to know is how much interest does the account earn after 4 years, so our time is going to be 4. First thing we'll do is find out how much total money is in the account, and then we'll figure out the difference between the starting amount, 3,000, and how much we ended with. So A equals 3,000 multiplied by 1 plus 0.0125 divided by 12 to the power of 12 times 4. And again, I work inside those parentheses first. So 0.0125, I'm going to divide that by 12. That gives me my fraction, and then I'll go ahead and just add 1 now, and I get 1.001 approximately to the power of 48. So I take this and raise it to the power of 48, and I get 1.0512. So 3,000 times 1.0512, and then we multiply to find our ending balance. 3,153.73. This is the total balance of the account after 4 years. But what they want to know is how much interest does the account accrue. So if I'm ending with $3,153 and I subtract the beginning amount, what I'm going to find is that the interest, or the amount of money that the bank gave us, was the difference, which was $153.73. That brings us to the end of our video today. Thanks so much for watching, and have a great rest of your day.